Okay. Let me sound loud. All right, here we are. We got not much time left. This is we have 4 lectures to go here. We're gonna finish talking about the Rangakata method. This is an enormously important tool. This is used all the time for tons of stuff. Like this is the main MATLAB ODE 45, which is the command that many people use. ODE 45 in MATLAB is using a 4-5 Rangakata method. So this is a big one. So we're going to just finish talking about that today. We're going to talk about some multi-step methods, and then we're going to talk about stiff differential equations, and then we are done. And we will have a review on Monday. I have the final exam written. I will post the first 2 pages of the final exam, which consists of the cover sheet, which will allow you to see how many questions there are, equaling 10, and the point totals for each question, approximately 10, for a total of 100. And then also the formula sheet, to which I have added a few things. I don't believe, I mean, with the exception, I was thinking about this, with the exception of needing to know what is a cubic spline. Like I wrote down what the end conditions are for the clamped and natural, not a knot condition. The end can, like, what does that mean? But you have to know how to set up a cubic spline. I mean, there's not like do this instructions on the formula sheet. Other than that, I do not believe that there's anything of like any large thing that you would need to memorize. It would be rather obscure. Like I said, you need to be able to find Taylor series on your own. The remainder theorem is there, but you know, it doesn't tell you how to find a Taylor series. But let us do it this way. I will post that, and over the next few lectures, you can ask me, do I need to know X? And if it's not on the formula sheet and you need it, I will say yes. Okay. Yep. Will it be what? Yeah, I'm going to post an older final exam. I'll do that as well. Please be a bit cautious about that, because you know things are not always emphasized the same and whatever. But there's some, and I'm also not going to be posting solutions for that. I don't have time for that. Yep. I don't think we have a necessity for cumulative practice problems. Honestly, we have problems. We've done a lot of problems. Like my view of this is, if you want more problems to do, always a good strategy, solve more problems. What you should do is take a look at the problems that I've assigned. Make sure you can do all of those. Take a look at the examples in the lecture. Right? Make sure you can do those. If that's not enough, then look in the textbook and pick the ones that are odd, because you can check the answers in the back, and just do ones that are similar, you know, to the ones that we have, right? And then also another good strategy, look at some slightly more conceptual ones and say, you know, can I do this? Because oftentimes if you can do those, or above what we probably ask, that would be not the theory correct, right? What we want to avoid as much as possible is spending too much time focused on, like, what is the formula that, if she asks this, what formula should I use, right? That method doesn't usually work as well as, you know, do I understand what it is we're trying to do here? And then if the answer to that is yes, generally speaking, you figure out what kind of method and formula to use so you know what you're trying to do. Yeah. This is a sort of a different example of that when we are in Math 232 doing least squares fit. Okay. And we have some data, which we have, in fact, which is like your grade in Math 152 versus the number of hours that you study. And you get a scatter plot of all your students, right? And then you try to put best least squares fit through that. So I have many students in Math 232 asking me, which numbers do I put in the matrix to do this, to do a least squares fit? Tell me which numbers to put in the matrix to tell MATLAB to do this. And I'm like, no, but this is the wrong question, right? The right question is, like, what is it that I'm trying to do? Write out a small example, and then see, oh, I'm trying to solve this A equals B. There clearly this is A, right? And then you say, oh, I see, that's this data, right? Like just saying, I've got data, please tell me where to put it, is the kind of study you want to avoid, right? You want to avoid, what are we doing? And you know, could I at least plausibly regenerate the stuff for myself? Maybe with some help, because you wouldn't remember all the details, but you could but you can sort of follow through and understand where everything is coming from. Yep. I'll give a little bit more direction to, like, as the week is going, and on Monday review session, I'm gonna be pretty upfront about the sort of main topics and that sort of thing. I'm homing in on that. Yeah. Other questions like that? Okay, let's take a look where we were at. We had we were looking, and we went through a fairly arduous derivation. I just want to highlight what we were doing. Let's not worry about the details. What we did is we basically said, we came up here and we said, starting that again, sorry. What we were doing is we came and we said, given this idea. Given that we want to use two function evaluations in this manner to try to get a numeric solution to our differential equation, given that, what is the best choice for the unknown constants? That's what we did. We went through a whole pile of calculations, and we found out that at the end of the day, we had 3 constraints and we had 4 unknowns. That means we have a bit of a choice, right? We have more than one choice. Now, and then right up following to that, we wrote out what our 2 common choices. One's called midpoint rule and one's called the modified Euler. That's it. And so what we basically do is for both of those things, here, for example, is the modified Euler. We have an update rule. We start with our initial condition. We plot along using this rule, and we keep getting more and more points to the solution to our differential equation. And then we can plot them and have a look at that, or we can use those to calculate whatever we want. Okay? That's the program. It's not at the heart of it. Using this is not complicated at all. You're just making some calculations step by step as you go along. Okay, that's where we were. There are we did this for the Runge-Kutta method too, for which we have 2 function evaluations per step. For example, the most basic method we saw, Euler's method. How many function evaluations were there per step? Question repeated, being repeated. Euler's method. Again, Euler's method. How many function evaluations did you have to make per step? Okay, that didn't work well. We have here W naught is equal to y naught, which we would be thinking of as y at time t equals a, wherever that starts. And how do we find yi plus 1? How do we find that Euler's method? Okay, hang on just a sec. We have a differential equation. This is y of t I plus 1. I'm feeling like little hairs in the back of my neck going on. I'm still feeling hairs in the back of my neck going up. I need some help here in the front. It's okay. He's gonna try again. I'm asking for our most basic Euler's method. What function?
right? Yep, no, you're doing well over there. H, this is F at, this is now W1, where I'm giving up on the I's. I'm like, we have W0, and now we're just gonna see, how do we get the next one? We go F at, there. What's wrong with this? Sorry to put you on the spot, you're about to learn something. Or why you mean what? Right, okay, so this, what's wrong with this, and he has sussed that out for himself, which is great. This is not right because this is the solution. That's the exact solution. Let's keep track what this is. We don't know the exact solution. Why would we be using the exact solution? I don't know, man. If you use the exact solution, you don't need to. Okay, so no, we're not going to use y at all. And the idea is, of course, that we're always starting like this. We have a differential equation, which means we can calculate the derivative at any point. We have an equation for that. So we can always calculate the derivative. So we start with the initial approximation, and then we have an update rule, which allows us to calculate the next one over. So the idea here is we have an exact solution. There's my exact solution, y of t. Here's my initial value. That is, this is going to be at time t equals a. This guy here is y at a. It's also w at a. We know that, guys, so we set our first approximation to be exactly what it is at the beginning, and then we step over a distance h, and we somehow calculate this guy, w at a plus h. And we have a way for doing that. We call this w1. We call this w0. Okay, we have a way of doing that, and the Euler method of doing that is to take to calculate w1 from w0, going over a distance h and using the tangent line at this point here, actually. Let me just try to make this a little bit more realistic. So calculate the tangent line here, and we're going to make W1 right here. That's what we're doing. Okay, so we use the information that we have, the previous step, the step size, and then we make one function evaluation, and it is a computation of the derivative. Yeah? Excellent. How about the rest of you? Yes or no? Yes, this is key, right? So when I just off the top ask you, how many functions are you using? Yeah, right? We're trying to go from W0 to W1. We make one function evaluation. Okay, the program here is exactly the same. It's exactly the same. We have W0, and we want to calculate W1. Okay, now we're assuming I equals 2. You have W0, that's our initial condition. We want to calculate W1. Right? We're trying to figure out what we would like to do is get this guy right here. Right? But we don't know what that is. That's the exact solution. So we're going to come somewhere. Who knows? We're going to come as close as possible. But whatever method, this is the tangent line, nice and dry. You get W9. The Runge-Kutta method calculates this, and then combines them. How many function evaluations? First step. 2, right? It's a method. So let's ask this question. If h in Euler's method, if h was equal to 0.01, in the Euler method, what value of h would I choose here so that I need the same number of function evaluations? Get the same number of function evaluations. I want to get the same number of function evaluations. No, you can't do zero function evaluations. No, H not equal to zero, otherwise you're not moving at all. Huh? Thank you, 0.02, I completely agree with you. Right? Because I have to make twice as many evaluations per step. So I gotta make my step size bigger if I want to, at the end of the day, have made the same number of function evaluations. Yes, no, or maybe. Oh, let's draw a picture. Using Euler's method, using the Runge-Kutta method. I get W0. I get W0. This is Euler. This is Runge-Kutta. So here's the amazing thing, actually. If you took the collected works of Euler and you simply copied them out, copied them. I'm not talking understanding a single word of it. You just sat there like this, copying it. It would take you 8 years. All of it that came out of his head novel of research. 8 years just to copy it out. Only that he had 13 kids. Okay. Okay, here we are. Euler, Runge-Kutta. I go from here to here, an Euler, one function evaluation. I go over here, what did I say, 0.1, this distance here, 0.01. Okay. I go W2, and I move over 0.01, and I have made two function evaluations. Guess what the next one? Okay, 3, right? I go here, W3. Each step, I'm making one function evaluation. At the end of the day, I'll have made, let's just go like this. W4, don't know why there's gremlin. I'm gonna go one function evaluation to get to here, one to here, one to here, one to here, one to here. 1, 2, 3, 4, 5. Let's do one more so it's even. Okay, one to here. There. Okay, 6 function evaluations to go across, making an evaluation every 0.01. Now I'm here. I want to make 6 function evaluations. I cannot go like this, W1, W2 like that, because I'll get 12. Because each one moving over, like if I was doing like this is W1, this is W2. If I did that, the same distance, 0.01, it's 2 function evaluations to get to here, 2 more to get to here, that's going to give me 12. But if I want to be honest about how much calculations do I have to do when I compare these two methods, do the same number of calculations, then what I have to do is step over to here, W2, going 0.02, like that, and do that. That will be going from here to here, 2 function evaluations. Same as going from here to here to here to here. Have I said enough about this to make this clear? Yeah. Is it between what? Yes, it is. If it's the whole thing, if it's if it's right here, that is 0.02, that distance. But each Euler step, this one's 0.01 here, 0.01 here, 0.01, 0.01, 0.01. Each one of those is taking one function evaluation. Now we're going to go here, 0.02, 2 function evaluations, 0.02, 2 function evaluations. We're going to do half as many steps with twice as many function evaluations per step. So if we're going to look at the comparing methods based on how much work you have to do, you want to change the step. Okay. You'll be happy to know, there are higher order, runga, kata methods. I mean, these require more statements. That is the only, in some sense, different. We just saw the Euler method, or one statement method. There are roughly kata orders, two statement methods. Well, guess what? You can make 4 or 8 or 12 or how many function valuations you want and have a higher stage method. And you do the derivation exactly what I did for the two-stage method, except it looks dramatically more ugly, harder to keep track of, and takes a lot more pages to do. But it is exactly the same method. So we're not doing it. The third order one, Rangakata one, where you use 3 evaluations, 3 function evaluations per step, is in the textbook. We're not doing it. They're not used. The fourth order are very widely used, and it is tedious to do. And actually, in some sense, you really know what you're doing from the second order one. Not that much difficult. It's just tedious. It's just like, if you know how to multiply a 3 by 3 matrix, it's not hard to multiply a 12 by 12 one, but it just is annoying. So there you have it. The underlying idea is exactly the same. We're not doing it. But the most common example of a fourth order Runge-Kutta method is this one here, where the calculation, the update rule looks like this. You first calculate something we call K1, which you calculate by taking H times F at PI WI. Then you calculate K2, which is H times F at PI plus H over 2. WI plus A1 over 2. K3, which is H times F. You do not have to memorize this. Calculate K4. Okay, and then you calculate this for constants and your update rule. Looks like this. You take your previous approximation and you add together these guys here in this one. Okay. Plus something. Okay, how many functions are you? Oh. So I think so it takes 4 times the effort for each step on Euler's method. However, you get there faster. Okay, so it's more complex to figure this out. You can get a 5th order method. Whatever, it just keeps getting worse in terms of the algebra that you need to do, and it's actually not that common to use a method of orders greater than 4. Okay, so we're just going to take a look at how nicely this works. It's really a miracle, actually. So there's the code for the Runge-Kutta method is in Canvas, and we're just going to look at a graph here to suss out what's going on. And we've got here we're comparing here Euler's method with the midpoint method. That is the Runge-Kutta method order 2, and then the Runge-Kutta method order 4. Okay. So we've got our value t ranging between A and B like it normally does, and in this case A is 0 and B is 2. So we're asking for a solution for a differential function between 0 and 2. we have an initial condition. That is, we get told that y at 0 is equal to 1. Okay, and then we have a differential equation. There it is. Y prime is equal to 1 plus b over 1 plus y. Like always, that is this. F, F, Z. Okay. We run the three methods. We get the exact solution. We take the difference between the exact solution. We are calling here global error. What is global error? It looks like this. Global error is the maximum value of yi minus wi. So at each step, we're going to say we have the exact solution. And the value is the exact solution. At that value, we have the corresponding approximation of that x value, which is the fifth factor. Well, by this time, we'll do that on the whole. That's our global error. Okay, I is going from 0 to n. Global error is the order of the method. Okay, let's take a look at what happens. We do this little experiment. The blue line is Euler's method. So the dependent variable here is the number of function evaluations. Okay, so it's the step size. Okay, it's the step size, which of course means the number of function evaluations. Here is a order 1 method. Euler. Here is a order 2 method. Runge-Kutta method of order 2, and here's order equals 4. Runge-Kutta method of order 4. You can see that the slope of the line is the order of the method. We got 1, 2, and 4. You can see the Runge-Kutta method of order 4, the global error going down to close to machine epsilon right down here, with a step size that looks close to be, well, somewhere about 0.005. These guys still haven't reached machine epsilon. It's way better. Okay, so let's just take a look then at the same experiment, but we're looking now here instead of at the step size at the number of function evaluations. So you can see there the number of function evaluations for finish your Runge-Kutta method down to machine epsilon looks to be somewhere about 5,000. These guys at, this guy here at some 100,000 still hasn't finished. This guy is right out left field. You don't need Euler's method. Okay? The Runge-Kutta method is going to make making more function evaluations per step. You have to make a lot less steps and still get a better result. Good news. Bottom line is Runge-Kutta is good news. Questions about this? Okay, so we've got some remarks here. Runge-Kutta method 4 is the most accurate of the methods we've seen. The global error matches the order of the method. It's also the most efficient, and higher order method implies smaller global error. This is true in general. So given a method, here's our method. All our methods look like this. We start with an initial condition. We have an update rule. And our update rule is some step size times some function of Ti, Wi, and A. And all we've been doing in this program is saying, let's change that. All our methods look like this. if we take a look at the, local truncation error, which we compute in the following manner, yi plus one minus yi plus h times there. That's the local truncation order, error, and that will be some order h to the p plus one. That is, this is a method of order p. The local truncation error is h of p plus one. Then the global error. The global error is the maximum. We already wrote the previous slide. In I is 0 all the way to n of wi minus yi. That will be of order. Okay, your local truncation error is saying exactly what I have. I'm going to have to write one step, and one step in. That's your local truncation error. And then the global one is to look at what the maximum value is across the entire thing. And you usually lose that one. You lose the one. So global error is of a lower power. This is a theorem. This is a theorem 5. This is this and like this. So it's a theorem 5. Okay. That is the program. You've seen Euler's method, you've seen Runge-Kutta method of order 2 extensively, and I'm telling you there's a Runge-Kutta method of order 4. The difference is the update rules are different, you get different systems. Of the ones we've seen so far, Runge-Kutta method of order 4, clearly the best. All right, gets better, because what we can do is make an adaptive Runge-Kutta method. What is it? Stepping over with the concept is fine, but you know, there's some so we saw that adaptive quadrature. You can do exactly the same thing here. You can have an adaptive Runge-Kutta method, and you want to be able to do that automatically. You don't have to have any brain power into doing this. It should happen automatically. And what we did before, so recall adaptive quadrature. The general method is to use a eighth order method, and then use a p plus first order method to estimate the error. To estimate the error of this guy. Then use that to decide how much to step. To which interval basically. Okay, so we have come to the Runge-Kutta method. I'm simply telling you that you can make it adaptive in exactly the same way as the quadrature routines. And that is exactly what MATLAB does. ODE 45 uses a fourth order Runge-Kutta method, and it uses a fifth order Runge-Kutta method to estimate error and adaptively use the step value. Okay, and then there's another one in MATLAB, should you decide to use it, which is ODE 23, which does the same thing. The second order Runge-Kutta method it uses the third order length cut method in order to, this to the adaptive movement of your, this is very going to be good. Okay. Let's take a look at this, differential equation. Here it is. The bounded pole equation. There's the differential equation. There's the two initial conditions. So I'm going to write this in this manner, like this. Okay. Move that to the other side. Okay, I'm writing it like that because I am going to convert this into a system of initial value tests. It's a second order one. To not use the MACM. That is always the case even as you go higher order differential equations. So we're going to convert this into a differential of two first order equations. I'm going to make the variable y. So y will be, what do I put here in terms of u? U and u prime, absolutely. Okay. How am I thinking of this? I'm thinking I set y1 equal to u of t, the solution I'm looking for. And then I take y2 equal to y1 prime, and that's equal to u prime of t. The initial condition. What are the initial conditions here? For me? 1/2, 1/2. Okay. Initial conditions are this guy is u of 0 and u prime of 0. Okay. Then what is f of the big one? What do I put here? What's the first one? Wait. Okay, what is it? What is in this position here? What is that? We're moving in terms of in terms of our y square, right? There's two entries, I believe, on here in D, second entry. Okay, what is this right here? This is y1 prime. This is y2 prime. Right? This is the derivative. It's just a vector of the derivative. Now it's y1 prime and y2 prime. What is y1 prime? y2. That is y2. And what is y2 prime? Write that down. Y2 prime is u double prime. Right? Y2 prime is y2 double prime. Y2 double prime is, okay, let me do this. Y2 prime is u double prime of u. That is 1 minus u squared, u prime minus u. I am writing this in terms of y. This is 1 minus, what is u? Y1. And then what is u prime? Y2, exactly. And what is u? Sorry. I now have a differential equation, a system of differential equations. Let me just write this here like this. This guy, y1 prime, this guy, y2 prime. This is actually what I care about. Right, what do I care about? This guy, I'm trying to find this. But I have a system of differential equations. There's one differential equation, and there's the second differential equation. Okay, make sure that you can do this, right? You absolutely have to be able to take one of these second order things and make them two first order. Otherwise you can't use that either. Okay, so for sure I'm gonna ask you to do that. Okay, so you do this, you set up, I'm just gonna show you a little bit of MATLAB plan. You can set up, the options that you want to use, like you can take a look at the help documentation that tells you about this. Then you call, ODE 45, and this is your function. This is your F T Y. You have just figured out what that is. Then you have some other options, the time interval you want to solve the thing on, your initial constants like that, and whatever the options are that you set up here. Like you'll be actually further control over how this thing operates. Okay. Let's just talk about that, setting up that this function right here, that goes right here. We have some function f equal to van der Pol, PY. I do it like this. And then F1 is Y2, and F2 is 1 minus Y1 squared. I'm just not going to put that down in MATLAB. Do it properly. 2 star Y2 minus Y1. So if you enter in your function, and then you make it do the work, and you get the output. There it is, ODE 45. Apply to the difference, apply to the van der Pol equation. This is the solution to the van der Pol equation. This guy right here, the blue guy, is your Y1 at P, which is what you want, U at P. That is your solution. So that's your function equation. The other line here is, this guy here is U prime. That's the first derivative. And you can see the adaptive testing where the function is changing more. You can see like the more mesh plane. Adaptive mesh. You get statistics out from this thing. So you can MATLAB will tell you how many functional evaluations that I have to do in order to do this. Then you can see it from increasing the step size when the solution is rapidly changing. The power tool in MATLAB. Okay. That's it. That's the running setup. Okay, we'll have to start. We'll start with our multi-step on Wednesday.